Good morning. Looks like we're live and everything is up and running. I'm gonna go ahead and pause this preview window here, and I'll keep the chat up on a side window in case this chat isn't working, because that would that happened before and that was terrible. But as soon as somebody says good morning, then I'll go ahead and close my my phone down so I can just pay attention to the chat here. All right. Well, I don't really have anything interesting going on in the world that I noticed from the last since yesterday to today. So I'm just gonna go ahead and continue on with the we're in patterns match the structure of values. Although I realize that not the exact correct place. Here we go. In the patterns part of chapter 18, we are in the section refutability, whether a pattern might match to fail. Patterns come in two forms, refutable and irrefutable. Patterns that will match for any possible value passed are irrefutable. An example would be x in the statement, let x equals 5, because x matches anything and therefore cannot fail to match. Patterns that can fail to match for some possible value are refutable. An example would be sum x. In the expression, if let sum x equals a value, because if the value in the a value variable is none rather than sum, the sum x pattern will not match. Function parameters, let statements, and for loops can only accept irrefutable patterns because the program cannot do anything meaningful when values don't match. The if let and while let expressions only accept refutable patterns because by definition, they're intended to handle possible failure. The functionality of a conditional is in its ability to perform differently depending on success or failure. In general, you shouldn't have to worry about the distinction between refutable and irrefutable patterns. However, you do need to be familiar with the concept of refutability so you can respond when you see it in an error message. In those cases, you'll need to change either the pattern or the construct you're using the pattern with, depending on the intended behavior of the code. I mean, I kind of feel that there's been a lot of like the error messages are really good in Rust. What we've gotten so far in the example codes have been oh well, like you're not matching this potential pattern, and therefore we won't compile until you do. Let's look at an example of what happens when we try to use a refutable pattern where Rust requires an irrefutable pattern and vice versa. Listing 18.8 shows a let statement, but for the pattern we've specified, sum x, a refutable pattern. As you might expect, this code will not compile. Let sum x equals some option value. Right, because it's like there's a chance that it won't exist. If some option value was a none value, it would fail to match the pattern sum x, meaning the pattern is refutable. However, the let statement can only accept an irrefutable pattern because there is nothing valid the code can do with a none value. At compile time, Rust will complain that we've tried to use a refutable pattern where an irrefutable pattern is required. Yeah, refutable pattern and local binding, none at covered. And so like, even if I didn't know what refutable pattern was, it would show me and say like, hey, none, like there's a possibility of none being here and it's not covered by the code, meaning that, you know, what will you do if none happens? So like, I think that's something that that yes, knowing this would be helpful, but it's also not completely essential because the compiler messages are pretty dang good. Because we didn't cover and couldn't cover every valid value with a pattern sum x, Rust rightfully produces a compiler error. To fix the problem, where we have a refutable pattern where an irrefutable pattern is needed, we can change the code that uses the pattern. Instead of using let, we can use if let. Then, if the pattern doesn't match, the code will just skip the code. The code will just skip the code in the curly brackets, giving it a way to continue validly. Listing 18.9 shows how to fix the code. Listing 18.18. So yeah, this is where we then do if let sum x, and then we set equal to that. Because that way it's like, well, then just don't run this if there's a none value, because it won't pass this if. We've given the code an out. This code is perfectly valid, although it means we cannot use an irrefutable pattern without receiving an error. If we give if let a pattern that will always match, such as x, as shown in listing 18.10, it will not compile. So if let x equals 5. So what do we get here? Basically, irrefutable if let pattern, irrefutable pattern. So I mean, this might be a little bit more helpful to understand what irrefutable means, but what I'm seeing here is it still points to you and say, like, look, you can't do that. This is a normal let. A normal let x equals 5. There's no chance for it to ever fail. Why the heck use an if? For this reason, match arms must use refutable patterns, except for the last arm, which should match any remaining values with an irrefutable pattern. Rust allows us to use an irrefutable pattern in a match with only one arm, but the syntax isn't particularly useful and could be replaced with a simpler let statement. Now that you know where to use patterns and the difference between refutable and irrefutable patterns, let's cover all the syntax we can use to create patterns. All right, pattern syntax. Throughout the book, you've seen examples of many kinds of patterns. In this section, we gather all the syntax valid in patterns and discuss why you might want to use each one. All right, so we have matching literals. As you saw in Chapter 6, you can match patterns against literals directly. The following code gives some examples. So let x equals 1, match x. So it could be like, 1, 2, 3, or underscore. This code prints 1 because the value in x is 1. This syntax is useful when you want your code to take an action if it gets a particular concrete value. I mean, so that's obviously just plain old match. Matching named variables. Named variables are irrefutable patterns that match any value, and we've used them many times in the book. However, there is a complication when you use named variables and match expressions. Because match starts a new scope, variables declared as part of a pattern inside the match expression will shadow those with the same name outside the match construct, as is the case with all variables. In listing 18.10, we declare a variable named x with the value sum5 and a variable y with the value 10. We then create a match expression on the value x, look at the patterns in the match arms and the print line at the end, and try to figure out what the code will print before running this code or reading further. Okay, so we have our function main, let x equals, so sum5, let y equals just the literal 10. Then we do a match on x, so sum 50, which won't be it, so it moves on to the next one. Sum y, so that's interesting. It's going to catch the value of here, so we're going to get 5. So print line matched y equals, and then it's going to be 5, because that's the number gets put into here. So we don't even get a sum. It's not a sum this printing. We don't need the debug printing. And of course, the catch-all default case x equals, well, this won't run because this one will. And then afterwards, at the end, x equals, well, because we're in a block, nothing changed. So x is still a sum 5, and y is still a 10. Let's walk through what happens when a match expression runs. The pattern in the first match arm doesn't match the defined value of x, so the code continues. The pattern in a second match arm introduces a new variable named y that will match any variable inside of a sum value. Because we're in a new scope inside the match expression, this is a new y variable, not the y we declared at the beginning with the value 10. This new y binding will match any value inside of sum, which is what we have in x. Therefore, this new y binds to the inner value of the sum in x. That value is 5, so the expression for that arm executes and prints matched y equals 5. If x had been a none value instead of a sum 5, the patterns in the first two arms would not have matched, so the pattern would have matched to the underscore. We didn't introduce the x variable in the pattern of the underscore arm, so the x in the expression is still the outer x that hasn't been shadowed. In this hypothetical case, the match would print default case x equals none. When the match expression is done, its scope ends, and so does the out scope of the inner y. The last print line produces at the end x equals sum 5 and y equals 10. To create a match expression that compares the values of the outer x and y, rather than introducing a shadowed variable, we would need to use a match guard conditional instead. We'll talk about match guards later in the extra conditionals with match guards section. Good morning, Stacking. Just tuned in, but isn't this stuff they already taught back in chapter 5 or 6, or am I missing something? No, this is exactly the stuff they taught back in 5 or 6. They're trying to they're trying to explain a little bit deeper about how it works behind the scenes. But I think part of it is because we went so deeply into the exercises and just didn't follow them shallowly, we kind of figured out a lot of this on our own. Which, I mean, I guess that's good. Multiple patterns. In match expressions, you can match multiple patterns using the pipe syntax, which means or. For example, the following code matches the value of x against the match arms, the first of which has an or option, meaning if the value of x matches either of the values in that arm's code will run. So I kind of feel weird about this. We had learned this like for, I think, the first, like the calculator thing that we had done, and I felt like really bad about just using a single pipe here, and it always trips me up because I'm just so used to, or if I'm going to use the pipe symbols, that it's two pipes. I kind of almost feel that I would have preferred, if we want to keep it something different, then just do really something different, like a -o for, you know, the way that Bash does it, or an actual or, the way that I think Lua does it, or just double pipes and just leave it that way. The fact that they take pride in copying C and then they don't copy double pipe is kind of strange. The thing is, they do copy double pipe in standard if statements. It just not in matches. It's just this is the thing that feels strange to me, is just in matches. Matching ranges of values with ... The ... syntax allows us to match an inclusive range of values. In the following code, when a pattern matches any of the values within the range, that arm will execute. All right, so this is nice. So we can have let x equals 5, 1 ... 5 will just match anything through 5 inclusively. That, if x is 1, 2, 3, 4, or 5. Okay, I noticed that they're using 3 dots instead of the 2. So is it 3 dots in a for loop? So if you do like for in, I'm gonna try to remember this. What's the like the Rust REPL? Oh yeah, we have a REPL that works. I haven't done much Rust, but I struggle to think of a use case where you would want to do this type of matching in a match statement. Yeah, I'm not sure either. Like these feel very very edge casey, or like, oh, it's probably going to be one of those things where I'm not going to be able to think about it until I run into it, and then I'm not going to be able to think about it again because I just use it so little. I've actually run into that a lot with teaching, where there are some important concepts, especially with like authentication and authorization, but I just don't remember like what the edge cases are that I need to like teach until it's too late. Then the students are all confused. Okay, so what I wanted to make sure was, if I do, so for I and 1, because I think this is just ... 15. It's not ... and I want to print line . So if I run this, it does just print these out, right? It's a double dot and a for loop. So, I mean, it's another thing where it's just one more character and it completely changes everything. 1, 2, 3, 4. If I add another dot here, what happens? Inclusive range syntax is experimental. Oh, so it's like only allowed in matches right now. That's what I'm seeing. So if we do something like that x equals the 5, and then we just match x, and then if we have essentially 0 ... 5 print line, we matched. That looks like it's also using nightly. Is this using nightly? Oh, 1.9. You're right. What do I tell it to not do that? I have actually no idea how to like configure what version of Rust to use. Use the official Rust playground. Got a message from Danny on Slack about questionable Twitch. Where did that go? Oh, I misspelled. Come watch me. I on my you have to worry about that suck. Just yanking your chain. Come watch me love as I learn patterns. Yes, that would be more questionable. Let's go to the actual Rust's playground. REPL is doing good if they're showing up first before this. Okay, so let's try debug stable version. That's what we want. Oh, interesting. They're using a my box. I don't need any of this. I just need to try let x equals 5 and match x 1 ... 5. You had to use the playground before. Oh wait, did it remember like my stuff? Because I don't have an account on it, so yeah, maybe that was my code. And then I want print line caught. So if I run this, pattern underscore not covered. Okay. So I'll need to cover the anything pattern. And I'll do print line. Nothing. So yeah, it's caught because it's inclusive in this case. And of course, if I do 2 dots, it'll probably will be very upset. Exclusive range symbol pattern syntax is experimental. So like that is thinking about that too, I guess. Most likely using local storage. Oh, that's actually pretty cool. So I guess like personally, I feel weird that this range syntax, like this inclusive range syntax, includes the end, whereas in the for loop, so in for I in 1.5, we have our print line. With this, we end up, it's non-inclusive. You can do 1.5, but then really? Okay, so I mean that works, but it feels like a separation. Yeah, you see the discrepancy. It just feels different. Like it feels, it's just like the pipe operator for checking the or in a match. It just feels like it's different because they wanted it to be different. One creates an iterator, then the other one is a pattern. And like, so my personal preference is, let's just make them vastly different, not just off by 1 character. So if x is 1, 2, 3, or 5, the first arm will match. The syntax is more convenient than using the or operator to express the same idea. Especially if we want to match, say, any number between 1 and 1000. I mean, so I guess if I wanted to use matches exclusively and not use a simple if, you know, if x is less than this, and greater than this, then maybe that would work. Like that's where I could use this dot. Ranges are only allowed with numeric values or char values. Okay, so char values might be more interesting because I could say like if, let's try that. So if x equals like the character a, or let's just do the character c, then and I do the character a dot character d. So that's still caught. So that I could see this being useful in this case, where you're just saying, hey, is this inside of here? But this probably won't work if I do like a and capital Z. Nothing. And can I do lowercase a to capital Z? Lower range bound must be less than or equal to upper. Oh, is it the other way around? Do I want to do capital A to lowercase z, I think. So, I mean, that's interesting. Although if I do that, I forget like what their characters between the actual letters. Is there something like left bracket is a character? Yeah, it is. So that gets caught too. I mean, it's not like you can replace this with a replace regular expressions with this. I mean, at least not easily. Here's an example of using ranges of char values. So C, so that's exactly the same thing. Rust can tell that C is within the first pattern's range and prints early ASCII letter. Does Rust have regex built in? You know, that's interesting because we haven't seen anything in the book. No, it does not. Oh, interesting. Destructuring to break apart values. We can also use patterns to destructure structs, enums, tuples, and references to use different parts of these values. Let's walk through each value. There is a regex. Great. I guess like not too surprising. It's the same thing with random numbers. They don't have a random number generator in a core code either. So destructuring structs, let point equals, let p equals point, x0, y7. I cheated and just used contained when I made my bot yesterday. I was using contained too, and it works. Or contains, yeah. It definitely works. Let point x a yb. Oh, so it's destructuring, but we're essentially we're capturing x and putting it into a. We're capturing y and putting it into b here. That's interesting. This code creates the variables a and b that matches the values x and y, fields of the p variable. This example shows the names of the variables in a pattern don't have to match the field names of the struct. But it's common to want the variable names to match the field names. Well, wait, do I have to? Like, can I do it more in the sort of a JavaScript style of destructuring? So if I say like, okay, I want to struct, we'll call it blah, and I just have, we'll do x and y. So maybe we'll just do location. We'll pretend that this is a vector. Not a Rust vector, but it's a sort of more of a game engine type of vector. Okay, so basically we're going to have an x and y location point. So x is going to be a I32, and y is going to be an I32. So we can create a new location. So let my location equals location, and we're gonna put x is let's do like 155 and y is 962. And then if I want to get, destructure these out, could I say, is it let, it's still let, oh, interesting. So it's let point equals, let point this equals p. Oh, interesting. Okay. This syntax, I didn't notice the point here to begin with. So it's gonna be let location. And then I have to do like, can I do x and y equals location, and then print line x y, x and y. Okay, so I mean, I can do destructuring without this. This is just for reassignment at that exact same time. This code creates the variable a and b, which match the values of x and y fields. Oh, we already went through this. Because having variable names match the fields is common, and because writing let point x xx, yy equals p contains a lot of duplication, there's a shorthand for patterns that match structs You only need to list the name of the struct field, and the variables created from the pattern will have the same names. Listing 813 shows code that behaves in the same way as the code in listing 1812, but the variables created in let pattern are x and y instead of a and b. So that's exactly what we did in our example. This code creates the variables x and y that match the x and y fields of the p variable. The outcome is that the variables x and y contain the values from the p struct. We can also destructure with literal values as part of the struct pattern rather than creating variables for all the fields. Doing so allows us to test some of the fields for particular values while creating variables to destructure the other fields. Listing 1814 shows a match expression that separates point values into three cases. Points that lie directly in x. Okay. That p equals point this, and then point. So this is destructuring straight, okay, straight into the match. Also, this is saying like, this is matching it like any x, but only if also the y is a 0. So any y if x is a 0, and then any x and y. So, I mean, those are also interesting. The first arm will match any point that lies in the x-axis by specifying that the y field matches if the value matches the literal 0. The pattern still creates an x variable that we can use in the code for this arm. Similarly, the second arm matches any point on the y-axis by specifying that the x field matches if its values is 0 and creates a variable y for the value of the y field. The third arm doesn't specify any literals, so it matches any other point and creates variables for both the y and x and y fields. Okay. In this example, the value p, it will match, obviously, this one. Destructuring enums. We've destructured enums earlier in the book. For example, when we destructured option I32 in listing 6.5 in chapter 6. One detail we haven't mentioned explicitly is that the pattern to destructure an enum should correspond to the way the data stored within the enum is defined. As an example, in listing 1815, we use the message enum from listing 6.2 and write a match with patterns that will destructure each inner value. So we have enum message. It has a quit, move. That has to be an a struct, so an enum struct. An x that's an I32, y that's an I32. A write that's a string, and a change color, which is a tuple. So let message equals message, change color, and we pass it, the three numbers. Then we match on message. So message, if message is quit, if message is move, and then we have the x and the y. So this is the destructuring right here. And so it's going to be the same thing with change color. It's R, B, and G. So yeah, that's the method of destructuring here. Kind of just went through this. I'm feeling less inclined to read everything in this chapter because I feel a lot of it we've already gone over in the book. Destructuring references. When the value we're matching to our pattern contains a reference, we need to destructure the reference from the value, which we can do by specifying an ampersand in the pattern. Doing so lets us. So is that destructuring or dereferencing? I feel like we need the beating the horse, dead horse gif. I mean, so yeah, is this destructuring or dereferencing? I guess it's taking a reference and okay, I thought this was passing a reference, essentially. So we're just taking point Let sum of squares equals I32 points dot iter dot map. We have our closure, and this takes in, I thought it was going to be a reference to point xy. Oh, well, so it's a reference to point, but then we're destructuring the point struct here. I understand this book is for someone who never touched a line of code, so it makes sense they kind of say the same thing over and over and over again in different words. I feel like this is the first chapter that's really repeating itself, though. I can understand that like earlier on. Okay. Had we not included the ampersand and point, we get a mismatch error because editor would then iterate over references to the items rather than the actual values. Okay, so basically we need this to get rid of that. Oh, I accidentally touched a button on my mouse. It's a chicken and egg thing. Talk about other things you have to use before learning it. The weird thing is how late in a book this chapter is. I know, I kind of feel that this would have been, instead of like an actual chapter, I feel like these would have been better in the chapters where they introduced them as just sort of like an extra page at the very end. Destructuring structs and tuples. So let feet inches point. So yeah, this is the same thing. Tuples destructuring is just like, you know, AB and then AB. So we have that. Ignoring values in a pattern. You've seen that it's sometimes useful to ignore values in a pattern, such as the last arm of a match. Oh yeah, so basically we could ignore in destructuring with the underscore. Ignoring parts of a value with a nested underscore. So is that just this? Some underscore, some underscore. So if it's a tuple, then, and they're both sums, then we'll just do that. And since we're matching this tuple right here, then yeah, both these will match right here. The fact that the scroll bar is not moving, I'm assuming this chapter is literally just rephrasing the whole book. It feels like it. It's at the halfway point now. Ignoring an unused variable by starting its name with underscore. Well, okay, the compiler has told us to do that before too. Ignoring remaining parts of a value with dot dot. So we've definitely done that with what was it? It was printing out parts of a string. Underscore rules are pretty straightforward, but dot dot is a good one to know. I mean, so the big thing is, so okay, so point, we match point, and then x matches any x, and then just ignores everything else so we don't have to match it. We list the x value and then just include the dot dot pattern. This is quicker than having to list y underscore and z underscore. Okay, so I mean that makes sense too. Also, like we have seen using this, which is first and last, to ignore everything in the middle. Also, like, so if you do without this dot dot last, it ignores everything from the beginning to the end. The funny part, doesn't dot dot in a struct mean copy the rest of the struct? Well, this is essentially matching. It's a pattern match. It just, in a match, it basically means ignore. But when copying, it means actually include. In this case, okay, so I think we've got this. Creating references and patterns with ref and ref mute. Let's look at using ref to make references so ownership of values isn't moved to variables in the pattern. Usually when you match against a pattern, the variables introduced by the pattern are bound to a value. That robot name equals some string from Boars. So match robot name, some name, print line, found a name, none is none. Okay. Oh, right. So we've done this once before with the ref thing. So basically we're getting a reference to name here. Instead of getting a full, instead of moving ownership into it. So that way we can still use this here. And then ref mute name so we can change it. Didn't they remove the words ref from Rust like 3 versions ago? It's a good question. Do we need that? Let's actually try running this. It's still there, it just tries to auto insert it. So if I run this, it should work, right? Account name Boars, but if I remove ref and run it, use a partially moved value robot name. I literally watched the video 2 days ago where someone told you they removed it. What's interesting is that this debug stable, what version? 127.2. So this is actually like the real stable version of Rust that's being run here. And ref apparently is still needed. So it's not been removed. It apparently has still there and needed. The playground is updated as part of the, yes, so I see that. It just looks like you do need it in order to prevent the fully moving in. So it will still error out here if you don't have this ref. Which means we're going to need the ref mute as well in order to then like make changes to it. Extra conditionals with match guards. A match guard is a conditional if condition specified after the pattern in a match. So wait, match num some x if x is less than 5. Oh, I think we use this also in calculator. So like we can get the sum x if x is less than 5. Otherwise, just get any x in the sum. Of course, none is also caught. There's a lot of text to explain that. I don't like that either. Okay. Bindings. The at operator lets us create a variable that holds a value at the same time we're testing that value to see whether or not it matches the pattern. So at bindings. A message hello ID field is within the range of 3 to 7, but we also want to bind the value to the variable ID variable so we can use it in the code associated with the arm. So we have an enum message hello ID 32, that message hello ID 5. Okay. Match on message. So message hello ID variable at 3 to 7. Oh, so it's just like kind of a destructuring ID variable from this enum struct, and then whatever is matching in here goes into ID variable. Now we have this one, match hello ID, but like ID is not an actual variable. So this is a way where we can then use it as a variable. Did your internet die again? Let's check. Maybe because I'm not showing any dropped frames at all right now. This example will print found an ID in range 5 by specifying ID variable at before the range. Okay, so basically it's just a way for us to capture what it was that was caught here in the inclusive range and stuff that result into an ID variable. And guess what? We reached the summary of chapter 18. So this was a long one, and we pretty much just zoomed through it because a lot of it was repeating what we had done earlier. And we just sort of looked at the examples. We didn't actually store any of the code in the repo. I didn't really feel any need for that. But let's go through the summary here, and then we'll maybe set ourselves up for next tomorrow morning. Rust patterns are very useful in that they help distinguish between different kinds of data. When used in match expressions, Rust ensures your patterns cover every possible value, or your program won't compile. Patterns in let statements and function parameters make those constructs more useful, enabling the destructuring of values into smaller parts at the same time as assigning to variables. We can create simple or complex patterns to suit our needs. Next, for the penultimate chapter of the book, we'll look at some advanced aspects of a variety of Rust features. This chapter might serve a better appendix page. Yeah, that's also true. It might be a really good appendix where it's just like, hey, let's just talk about more stuff. So what's going to happen here in advanced features? By now, you've learned the most commonly used parts of the Rust programming language. Before we do one more project in chapter 20, we'll look at a few aspects of the language you might run into every once in a while. You can use this chapter as a reference for when you encounter any unknowns when using Rust. The features you'll learn to use in this chapter are useful in very specific situations. Although you might not reach for them very often, we want to make sure you have a grasp of all the features Rust has to offer. So in this chapter, we'll cover Unsafe Rust. So how to opt out of some of Rust guarantees and take responsibility for manually upholding those guarantees. This is something that was talked about in the last Rust meetup here in Denver. What was interesting was that somebody said, like, yeah, so if you use Rust, unsafe, make sure that you only do it for like one line at a time. Because what I've seen is like a bunch of people just calling, okay, I'm gonna have an unsafe block here, don't check for memory safety, and then just like all the code. And that's not really helpful. Advanced lifetimes, syntax for complex lifetime situations, advanced traits, associated types, default type parameters, fully qualified syntax and super traits, and the new type pattern in relation to traits. Advanced types, more about the new type pattern, type aliases, the never type, and dynamically sized types. Advanced functions and closures, function pointers, and returning closures. So that I can create like a factory function that returns another function, or a higher order function that returns a function. It's a panoply of Rust features with something for everyone. Let's dive in. Oh, it's back. You have no idea what's going. Oh, do you have Comcast? I have Comcast too, but like it's there. There's no drop frames for me right now, so it might be on your side. I've noticed also sometimes, like if you have browsers that have been on for a really long time with streaming services, things can get really weird. Which is, I guess, just a way of saying maybe a reboot would solve it. But I'm gonna save starting with this for next time because this is a long chapter. It's probably gonna take the entire time next time because we're going to, I'm guessing, actually do some of these examples and see the difference when we run it with unsafe and without. So let's go ahead and update where we're at. So Unsafe Rust. Actually, it's not. GitHub, we want to open up you. Okay, so we're at Unsafe Rust, and specifically, we're at this URL. Got through chapter 18, no code needed to be added here. Let's go ahead and send that on up to GitHub. Okay, thank you, VS Code. I don't need to share my screen. Okay, so that should have updated there. So we have everything should be on GitHub now. Let's see, what else do I need to do to like set up for tomorrow morning? I don't really think necessarily anything. We're gonna continue on. We're going to learn this Unsafe Rust, and we're getting really close to being able to do that project. Now I do have an emergency trip I have to take out to my family next week, starting on Monday. So I'll be back on Thursday next week. But I'll send out tweets and on those specific days. I won't be able to stream because I won't have good enough internet to do so. So I won't go through the book, but I'll be doing other things. So if you want to follow me on GitHub, you can see whatever interesting things I do. Hopefully nothing serious. I'm hoping so too. But I'll find out more when I get there, and we'll see how things are. But I'll definitely be back on Thursday, and then we can just continue on with the book and and everything else. So with that, I'm gonna go ahead and call it a morning. Go ahead and get ready for the rest of my day. I hope you all have a great rest of your days. And I'll see you tomorrow morning at 7 a.m. Mountain Time. We'll be going through Unsafe Rust.